Okay, students. So this is lecture number 3 in our um, thermodynamics and electrochemistry lecture series. Now, what we want to discuss today is the use of another parameter, enthalpy, symbolized by H, instead of U or delta U, which represent the internal energy and internal energy change, respectively. The fact is, in chemistry and our biochemistry, most reactions, a matter of fact, overall in nature, most reactions occur under constant pressure conditions rather than under constant volume conditions. Now, enthalpy is a parameter that relates mainly to constant pressure conditions. That is, enthalpy is energy transferred at constant pressure, as can be seen here. Let me just get a pointer here, right? Hence, the heat change at constant pressure is called enthalpy change. So that's a simple working definition of enthalpy and enthalpy change. So enthalpy change is the heat change at constant pressure, whereas enthalpy, which is the absolute value, is the heat transferred under constant pressure conditions. Of course, you would say to me, then you're probably thinking then, okay, enthalpy change, delta H, is H final minus H initial. True, but it is also equal to Q at constant pressure, the subscript P meaning constant pressure. So enthalpy change is really the heat change at constant pressure as represented here. And this is a very simple general working definition. A more involved definition can be derived. Now, since delta H is equal to Q at constant pressure, and we know that U, which is the internal energy, is equal to Q minus PV, we can rearrange this expression such that Q is the subject. Q is equal to U plus PV then. We know that H is equal to Q, so we can write now H is equal to U plus PV. This is basically telling us that the enthalpy of a substance is the sum of its internal energy and the product of pressure and volume under which that substance exists. Now, the fact is, most of the times, we don't use absolute enthalpy values. Instead, we look at enthalpy change, all right, which is delta H. And so this expression, which says H is equal to U plus PV, must be differentiated. Now, to differentiate U, that is quite simple. It's just U final minus U initial. And so we can easily write delta U. So delta H is equal to delta U. But we must consider the differential of the product, PV. Now, I came up with a simple way, or what I think is a simple way of differentiating the product, PV. Let's say you have a rectangle, and one side has a length P, and the other side has a length V. If you decide to extend the side which has a length of P by a small amount, delta P, then you will end up with a new area represented by, or enclosed, I should say, by this green dashed line. Whereas if you decide to extend the side called V by a small amount, delta V, then you end up with a new area enclosed by this purple line. And also you'll have this excess piece which is enclosed by this red dashed line. Now, what is the area of this part that is enclosed by the green dashed line? Well, the area of that part, well, the area of any rectangle is side times side. The length of this side is V, whereas the length of this side here is delta V. Okay? Delta P, I should say, right? Delta P. So the length of this side is V, whereas the length of this one here, right, is delta P. Okay? So the area of this piece is V delta P. Here it is. Okay? What is the area of the bit enclosed by the purple dashed line? Well, the length of this side is P, whereas the length of this side is delta V. So the area for this purple bit, or the bit enclosed by the purple line, is P delta V. Here it is. What is the area of this part which is enclosed by this red dashed line or the red dashed lines? Well, the length of this side is delta V, whereas the length of this side is delta P. And so the area of this bit is delta P delta V. Now, this tells us that delta H is equal to delta U plus, right, the combinations of the differential of the product, of the different parts of the product. So we could put delta outside and put V delta P inside the brackets. Now this is the equation for delta H when U, P, and V are all changing. Okay? Now consider a situation where the pressure is constant. Right? What if the pressure is constant? Well, if the pressure is constant, then that means that delta P is 0, right, in the expression. So this part will become 0. If delta P here is 0 as well, 0 times delta V is also 0. So this part will be 0, and this part here will be 0. And so the expression comes down to delta H is equal to delta U plus P delta V. So under constant pressure conditions, delta H is equal to delta U plus P delta V. Okay? Now we can do a little proof if we want. Remember that delta U is equal to Q minus P delta V. Okay? Right, remember that. Okay. Now, if we should do a substitution, alright, if we should take up all of this part here, yes, let's have a look, let's highlight it. If we should take up this part, right, and substitute it here, what you'll find is this one. There will be cancellation because the minus P delta V would cancel with the positive P delta V as can be seen down here. And so what you find is that delta H is equal to Q at constant pressure. Right? And that is just proof. That is just proof that delta H is equal to the heat change at constant pressure. Now, it follows also that when the volume is constant and the pressure varies, delta H is equal to delta U plus V delta P. Okay? Because if the pressure is constant, okay, if the pressure is constant, then this part will be 0. Alright? Pressure is constant. So let's go back here. So let's say the volume is constant, I should say, sorry. The volume is constant, but the pressure is changing. Let's go back and have a look. Volume constant, pressure is changing, then this part will disappear. Right? And this part will also disappear. Okay? That is if the pressure is varying and the volume is constant. Okay? Now, enthalpy of a substance will of course have some properties that are similar to those of internal energy. Think about it. Remember, the enthalpy change or the enthalpy is really the sum of the internal energy of the substance plus the effect of pressure and volume. And hence what you find is that enthalpy and internal energy are similar but not the same. Why is it that they are similar? Well, enthalpy is made up of internal energy plus the effect of pressure and volume. And that's why they are similar. Not the same, but they are similar. Okay? Now, so the thing is that enthalpy considers the effect of pressure and volume. Okay? Internal energy really doesn't. So that's why enthalpy is a more useful property. And also the fact that most reactions in nature and most reactions that you will do in your laboratory work will occur under constant pressure. And that makes enthalpy a bit more useful than delta U or U. Now, before we move on, we have to mention an interesting property about enthalpy, an interesting property that enthalpy has. And also internal energy has this property. And it's called, it's a property which allows a person who is making use of enthalpy change or internal energy change to consider only the initial and final states and not the path taken. All right? Such functions are referred to as state functions. So a function where only the final and initial states matter and not the pathway taken to get to these states. Alright, these are called state functions. So enthalpy, alright, and internal energy are state functions. Okay, and this allows the application of Hess's law to these functions. Okay, right. Now, of course, we have to define what we call, an unambiguous standard change in internal energy or enthalpy can be specified by defining standard initially and standard final states of the system. What do we mean by this standard state of a substance? Now, the standard state of a substance is when the substance is in its purest form at 1 bar pressure. All right. Furthermore, once somebody refer to something as being standard, we're thinking about 298 Kelvin. Okay. Right. Remember, 1 bar pressure is 100,000 pascals, which is a little bit smaller than 1 atmosphere, because 1 atmosphere is 101,325 pascals, but 1 bar is 100,000 pascals. So when you say that something is in its standard state, it means that that substance is in its purest form and it's under conditions of 298 Kelvin, right? And 1 bar of pressure. And so if we're talking about standard internal energy change, the symbol delta U normally has a superscript theta on it, as seen here. If we're talking about standard enthalpy change, then the symbol normally has that superscript theta on it. Okay? So that's important because we want to make use of this property, this state function. Now, enthalpy change for chemical reactions are very, very important. And we can calculate the enthalpy change for a chemical reaction. For example, this one here. If we know the enthalpies of formation or the standard enthalpies of formation for the reactants and products. Now, the standard enthalpy of formation for a substance is the energy change when 1 mole of that substance is formed from its elements in their reference states. And you will see what I'm talking about when I mention the term reference state. In that, I will define it later on. Okay? So enthalpy of formation, right, is the energy change when 1 mole of a substance is formed from its elements in their reference states. Okay, and of course the pressure has to be constant. So look at this reaction here. We have propane reacting with oxygen to produce carbon dioxide and water. We want to calculate the enthalpy change for this reaction. Okay? We have the enthalpy changes for propane, enthalpies of formation, I should say, for propane, enthalpy of formation for water, enthalpy of formation for carbon dioxide, and also for oxygen. And all of these are standard enthalpy changes. For oxygen, note that you have a value of 0. And this is because we consider oxygen, though it is a compound, but because it is made up of one element, or some people like to say, look, this is the lowest form that it can exist in, oxygen that is, then you end up with enthalpy of formation being 0. Okay, so it's almost like an element, or some people like to say atomic compound or elemental compound, because it's just 2 oxygen atoms. All right, so that's generally 0. Now, in calculating the enthalpy change for this reaction, of course, enthalpy change is final enthalpy minus initial enthalpy. But what do we mean by final enthalpy minus initial enthalpy? Well, we mean the sum of the enthalpies of the products, right? Considering the stoichiometric coefficient represented here by n. Stoichiometric coefficient has to do with the numbers that you put, or the coefficients that you put to balance the equation. Minus, right, the sum of the enthalpies of the reactants. Of course, considering the stoichiometric coefficients. And of course, all of that is equal to Q. Let's look at how we actually carry out this calculation. Okay, well, it's products minus reactants. We have 3 moles of carbon dioxide, okay, gas. So we have to say 3 moles times the enthalpy of formation, enthalpy change of formation for carbon dioxide. And that enthalpy change, as you realize here, it's per mole. Because remember, the definition of enthalpy of formation says is the energy change per mole. So it means that if you are looking at the formation of 3 moles of carbon dioxide, you have to multiply this number by 3. Hence, as you can see here, we are multiplying by 3. Now, we have to add to that the other product, which is water. And we have 4 moles of that. So we have to multiply the enthalpy change of formation for water by 4. And then we subtract from that, right, the reactants. Well, in this case, we have oxygen as a reactant. That one will be 0, so it's not included here. And propane, for propane, we have minus 103.9 kilojoules per mole, and we only have 1 mole of that in the expression. All right, in the equation, I should say. Okay? And then at the end of that, we realize that our enthalpy of reaction is minus 2,219.8, which some people normally, round off to about minus 2,220 kilojoules. Okay? So that's our enthalpy of reaction using enthalpy of formation data. All right, it's products minus reactants, but you have to give consideration for the stoichiometry. All right, or reaction coefficients. Now, standard enthalpy change. Now, for the combustion of propane, it has been found experimentally that when the reaction occurs at 1 bar pressure and the substances are in their standard states, the heat transferred, all right, is 2,220 kilojoules per mole per mole of propane burned. And so generally, even though you see us writing delta H is equal to minus 2,220 kilojoules, this reaction is when only 1 mole of propane is burned. Now, generally, once we are talking about standard enthalpy changes, it's 1 molar under conditions of 1 bar pressure, right, and 298 Kelvin. So even if I don't tell you the temperature, once I'm talking about standard enthalpy changes, it's 1 bar pressure, all right, and the temperature is 298 Kelvin. Now, there are many standard enthalpies of reaction. There are many, all right, and you can find them in tables all over the place. You have standard dissociation enthalpy of a substance, standard enthalpy change of solution, standard enthalpy change of vaporization, and there are many others. Right? Some people even tell you that there are standard enthalpy change of sublimation, neutralization, and there are many others. All right? Okay, and this is just to give you some other examples, just to give you a few other examples and to show you via equations what they mean. For example, look at the standard enthalpy change of vaporization of hydrogen oxide. All right, is what we generally call it water. So you have the liquid and it's converted to steam. All right, so you have water being converted to steam, and that requires 44 kilojoules per mole. So every mole of water that you are vaporizing, it requires 44 kilojoules. Okay. You could also look at sublimation. This is where ice is converted to water. And for every mole of ice that you convert, it requires 6.01 kilojoules per mole of ice. Okay? You could also have dissociation, right? Bond dissociation. For every mole of hydrogen molecule that you break down, it requires 435.9 kilojoules for every mole. All right? That is the standard enthalpy change of dissociation for hydrogen. Now, despite all of this, the most useful standard enthalpy is the standard enthalpy change of formation. It's very, very useful because you could use it in assessing the feasibility of reactions. All right? Now, one thing we have to know is that the definition of reaction enthalpy is, of course, based on the equation. This is the definition of reaction enthalpy. All right, a reaction enthalpy change. And generally, we use, you could see that it is represented by absolute enthalpy values and not enthalpy change. enthalpy changes. The thing is that it's very difficult to obtain absolute enthalpy values, and they tend to be quite arbitrary. All right, so they are difficult to work with and they are difficult to come by. And so what you find is that generally we don't use, or you don't find that absolute enthalpy values are used extensively. And so we mainly depend on the use of enthalpy changes and even internal energy changes. We use changes rather than absolute values. Okay? Now, the standard enthalpy of formation, right? Earlier we mentioned the idea of reference state. Now, the reference state of a substance is the state in which it is most stable. Usually, these are 1 bar pressure and 298 Kelvin. This is very similar to standard enthalpies or standard conditions, I should say. All right. So, for example, just to give you some little examples, carbon generally exists as a solid, mainly in the form of graphite. That's not the only form, but mainly in the form of graphite. It is more stable as a solid. Hydrogen generally exists as a gas at 1 bar pressure and 298 Kelvin. Phosphorus, a white solid. You have also red phosphorus, so just to point that out. Generally existing as a solid at 1 bar pressure and 298 Kelvin, whereas oxygen, as we know, generally under prevailing conditions, it exists as a gas. Okay? Right. Now, just to run something else by you, the enthalpy of formation, as defined earlier, is when 1 mole of a substance, for example, propane, is formed from its elements in their reference states. Okay? So when 1 mole of propane is formed from hydrogen gas and graphite, that is called, the value that you get, the heat change that you get under constant pressure is called the enthalpy of formation. All right? Let's say it again. When 1 mole of a substance is formed from its elements in their reference states, once the pressure is constant, okay, constant at 1 bar, that is called the enthalpy of formation. Look at this other case. Water is being formed from oxygen gas and hydrogen gas, all right, under standard conditions. 1 mole of water is formed. If you form 2 moles, you can't call it enthalpy of formation. That's something else. It's when 1 mole of the substance is formed. And it is important that you follow that. Okay? Here's another example, formation of carbon dioxide. Okay? Now, why are standard enthalpies of formation of substances more useful than other standard enthalpies? Well, with tabulated standard enthalpies of formation of substances, one can calculate the standard enthalpy of any reaction, all right, even if it cannot be carried out in practice. Standard enthalpies of formation give an idea of the relative stability of the structure of substances. Okay, and I'll show you an example shortly. All right, now to calculate enthalpies of reaction, knowing standard enthalpy of formation of the substances involved in the reaction, one can calculate the standard enthalpy of the reaction. For example, propane. Okay, if you know and we did this example just now, if you know the enthalpies of formation for the reactants and the products, you can easily calculate the enthalpy change for the reaction. Okay, now, and just to point out the whole idea of assessing stability using enthalpy values or enthalpy of formation values. So look at these two isomers, cis-2-butene and trans-2-butene. Okay, cis-2-butene and trans-2-butene. You can assess the stability of them. Okay, both of them are formed from carbon. They are formed from carbon and hydrogen. However, the enthalpy change of formation of cis-2-butene is larger, it is higher than the enthalpy change of formation of trans-2-butene. Okay? The fact that the enthalpy change of formation of cis-2-butene is higher than that of trans-2-butene, it tells us that cis-2-butene is less stable than trans-2-butene. Why is it that cis-2-butene is a little bit unstable, or is less stable rather than trans 2-butene? Well, this is because of repulsive steric interactions between the methyl groups which are located on the same side. Okay, look at the two of them. In trans 2-butene, the methyl groups are quite far from each other, whereas in cis 2-butene, they are quite close. And so you have repulsive interactions in cis 2-butene, which reduces its stability. So just by looking at the standard enthalpies of formation, you can tell which isomer is more stable. All right, and the one with the lowest enthalpy of formation is more stable. Okay, and these are just some units, and that you can just glance over. Right, we know forces in newtons, pressure in pascals, energy in joules, power in watts, length, we normally measure length in meters, or mass in kilograms and stuff like that. So these are just some stuff for you to basically glance over. All right.